our question is consider the network and figure that switch open at t equal to 0. So when t equal to 0, the switch close and the capacitor act of open circuit. So first we apply mesh analysis in the loops between the capacitor to get the currents I1 and I2. So first we apply for the first loop, and then for the second loop. Then after that we solve it and we get the current one I1 and I2. Then after that we apply KVL to get the initial voltage, which is equal to 10 volts. Yeah.
So this V0 is actually the one in the capacitor place. So we find the V0 here, and the result is 10 volt.
Then after that our switch is open, so the T is bigger than 0. So we get the voltage after the switch is opened, which is equal to 5 volts.
Oh, yeah. So actually the switch is right up here. So when the switch is open, this part gone, become this circuit here. And then we can find the V0 right after the switch is open, which is 5.
Okay.
And then should I continue? Okay. At time infinity, that means until steady state, the capacitor will not give out any power anymore. So we will dismiss the capacitor here. So the circuit become this one. So the only thing powering the circuit is the 12
Wait.
source.
You are doing number
5,
right? Why is your problem like that? Yeah.
We are looking for the initial voltage and then steady state voltage.
Yeah.
Then we will.
You are looking at t equal to 0 before when t equal to 0, it is switched off, right?
Yes.
So why is this?
Oh, this 10 volt.
Why is this here? It's located here, yeah, V output. Yeah, the switch is actually here. The switch is here.
Yes.
Yeah, the switch is there, right?
This is the capacitor, sir.
Capacitor, sir.
Oh, the capacitor. Okay.
Yes.
Yeah.
And then the bottom one, this one. This is also the capacitor, but I misdraw it because source.
This is before it is switched off. Is it?
Yes.
Yes. Okay. Okay. Good. Continue.
This is when switched off, and then we can find the initial voltage in the 2 ohm resistor, and then after we switch off, the circuit will go through transient period where until it reaches steady state. When it reaches steady state, the capacitor will not give out any more power, so we can directly dismiss the capacitor here. So the only thing powering the circuit is the 12 voltage power source.
Okay.
With the 12 voltage power source, we can calculate the voltage in 2 ohm resistor at time infinity. And the result is 4.8. And then the next part is we are looking for the time constant. How to remove the annotator?
Oh, yeah. Sorry, you have to re-erase it. You can erase it actually. Annotate, clear all drawing.
Okay.
Yeah.
Now, where is it? Okay, here we are looking for the time constant here. So for the time constant, we can calculate the total resistor from the capacitor. So it will be like this one, the circuit here.
Okay, okay.
And then the total resistance is 4 over 5 ohm.
Yeah.
So and then the time constant is R times C. So 4 over 5 times 2, the capacitor value, and then become 8 over 5 seconds.
Okay.
And then we can take every value from before and put it in the general formula. And then we will get the result in the end.
Okay. That is the result, yeah, 24 volts over 5. Yeah. From K1, yeah, that is K1.
Yes.
And then K2 is there. Okay. Thank you very much, group 5. Let's roll the dice again for the next group. Group 6. Group 6 is who?
Me and Hanif, sir.
Eh, me.
Jesse and Hanif.
Jesse and Hani. Okay. Yeah, group 6, you may start presenting. Please turn on your video.
Okay. Okay. There. How do I remove the virtual background?
Okay, quick.
Uh.
Time is ticking.
Okay, I'll go first. Yeah. Okay. So here, we are going first. We are going to find the tau for in the circuit. So we are going to use the KVL here.
Can you
So,
please zoom in, yeah, because it's a bit too small, yeah.
So we're going to use the KVL here. So from minus 2 volt plus IR and so on until the 2 resistor. Then we're going to find the equation here. So we can see that the tau is 0.5 and it is equals to 6 volts. And since we have got since 6 volt is also the K1, here in step 2 we can use the steady state analysis to find K1, and which is K1 is equals to the voltage, which when it is in time equals to infinite. So when we insert infinite in the formula we found in step 1, we got the voltage for K1 is 6 volt.
Yep.
Yep. So the step 3 is to finding the initial value. So what we are going to do here is using the Thevenin's equivalent because the circuit is a bit complex. So as we know that if there is a forcing function from the voltage source, so that means the inductor will be short-circuited. So we short-circuit the inductor, and also we make the Thevenin equivalent. We get the RTH here. And also we apply the KVL. So we find the current that is going through here. So after that, we find the current equals 4 ampere, and we do the KVL again to determine the VO. So just simply input it, the equation, the KVL, and also the value of current, and we get the VO equals 4 volt. So the I here equals 4 over 3 ohm. So that means it's 4.4 over 3 ampere current going through here. And if you want to find the current, wait, I think it should be voltage, yeah. Yeah, I think it should be voltage. So the voltage is equal to the current 4 over 3 times 2. So it equals 8.88
yeah?
over 3. Yeah, it should be
so
voltage.
Please correct it later for the submitted answer. Yeah?
Yep, it's 8 over 3. So K1 plus K2 also equals 8/3 equals 6 minus K2. So K2 is equal to 10/3. So we get the K1 here equals 6 volt, and also we get the K2 equals minus 10/3, because this one is 8/3. So if we change it, it's going to be minus 10/3. So 6 minus 10/3 E raised to the power of minus t over 0.5 volts.
Okay, well done. Thank you, group 6.
Yep.
Okay, let's roll the dice again. Group 4 now. So group 4 is, who is group 4? Is group 4?
Michelle and Nikki.
Yeah, Michelle and Nikki. Okay, so please turn on your video and present your answer. Michelle and Nikki.
Oh, okay, sir. Wait.
Okay, can you please zoom in? So
Wait.
yes, if you can, yes, that's really nice. So number 4, yeah. Okay, so please present. Time is ticking.
So the first step, you have to.
Can you please zoom in? Yeah, it is very difficult to read with that. Zoom into 100% or 125%, please.
Wait. This.
Larger, please.
Larger.
Yes. So if possible, it fills the whole shared screen area. So if you could also hide the menu there, export PDF, edit PDF, etc. Even better, yeah. So then you can use view, then read menu, view, then page display, yeah, read mode. Oh, yes, that would be nice.
So the first step, you short the inductor and then you use KCL. So IL 0 minus is 12 volts over 2 k ohm minus 6 volts over 3 k ohms, and you will get 4 milliamps. And then when you open the switch, when you open the switch and redraw the circuit, you can use this formula, and then you use node analysis or KCL. So VT minus 0, this should be the ground, over 2 k ohms plus IT here, and then plus VT plus 6 over 3 k ohm is
VT plus
0.
6 or VT minus 6? Yeah. Oh, because it is minus, yeah, minus 6 volt, yeah, towards 0.
Yes.
Yes.
Yes. Okay.
And then you can simplify the formula, and then you get this 2.5 VT plus 3 times 10 to the power of 3 IT is minus 6. Nick?
Next, we could find tau and K1 from equation number, from the first equation, but I use another way. I am not finding tau. I find D. D is what this one, negative 0.2 times 10 to the power of 6. Next. And then we try to make I with the time of infinity. So when time is infinity, the
So what is the tau now? Is the tau been found?
No, sir.
Not yet. Okay.
After we try to use I in when time is infinite, the current will be negative 6 over 3k because the I direction should be upward, so it is negative. So the I in when time is infinite is negative 2 milliampere. Next.
Yeah.
So when I is infinite, we use K1 e to the power of negative, e to the power of negative. We are not using tau, we are using another formula. So after we find D, not tau. So this one, K1 is equal to e to the power of something. This something is not tau, but this something is D. Below.
It is not wise for the moment to use different form of equation. It's better to use the standard form of equation.
Yeah, because
after you write the equation in the form of tau dx dt plus x equals to f, then immediately you can know that the solution will be x equals to k1 plus k2 exponent minus t over tau. Yeah. Otherwise, then it will be confusing for you also, for the audience, including me. Yeah. For now, it is best to use the standard form. Yeah.
Because I learned this from YouTube, sir. I'm sorry.
Yeah. First is you use my method first. Later you can relate on your own, but for now, please use the standard form. Yeah, and using tau. Okay.
Okay. So later we submit the method using tau, right?
Okay, we will change it to tau.
What is the final?
Before we submit it.
What is the answer? Final answer?
This one is the final answer.
Minus
I
2
see it.
plus 6 exponent
Plus
minus
6 e to the power t over 5 times 10 to the power of 26 milliamps.
Milliampere. Yeah. Okay, thank you, group 4.
Okay, thank you, sir.
Yeah, good job. But yeah, for now, let's stick with the standard form first, yeah, so that you are used to it. Later, if you would like to be creative in the future, I'm not saying that I'm limiting, has to be with the current method, but so that everyone can understand also. So let's stick with the standard form for the while. So express first the equation in terms of standard differential equation. Tau dx dt plus xt equals to f. Then the standard solution will be xt equals to k1 plus k2 exponent minus t0 over tau. If t0 is 0, then exponent minus t over tau. Okay, everyone? So that later when we get used to it and we get mastery over the concept, then we may use different notation, different things, yeah. Okay, so let's roll the dice again. So 3 groups are left. Yeah. Group 3. Group 3 is Dave and Dimas. Please start on the video and share your screen.
Can can you see the screen clearly?
Yes, you can. I can.
Okay, so I will explain first. This is the schematic of the circuit, and the question asks, what is the current I1 as a function of time at the transient condition when the switch change. Now, first of all, at t bigger than 0, when it's already unplugged, so 12 volt here is uh, uh, we can leave the 12 volt behind because it is not connected with this loop here. Now use KVL at the loop shown here because I1 and I2 is now the same current, so we will just leave I2 behind, and so VL, which is the voltage at inductor, plus C at 6 I1 plus 12 I1 equal to 0, and so we know that VL, the formula is L times di divided by dt, and the I here is I1. And so we plug the formula into the KVL equation, and so we find this equation. Now we will need to times it with 1 divided by 18, and we will get this form, which will then explains that this is the time constant, and also this is the K1, means that this is a free response circuit. And so next will be explained by Dimas.
So the next step is to find the K2. We use the condition of where t equals to 0 minus. First, we have to find the current. So here the resistor is parallel. So we use this calculation. We find the resistor parallel is 4 ohm. Then we count the total of the current, and the current is 3 ampere. And from the circuit, the inductor becomes short circuit. Then we use current divider to find I1. Then we find the K2 equals to 1 ampere. Then ini tadi udah belum?
Ini belum. Ini yang
Tahunya?
Nggak apa-apa.
Okay, so from this equation we can determine the tau. The tau is 1/9. Then we use the general equation and substitute the apa sih namanya? The number. And the final result is I1 equals to E to the power of minus 90 ampere at t larger than 0.
Okay, yeah, well done. Group 3, yeah, I think it's okay, correct. So let's go to the next group. So just left group 1 and group 2 left. Yes, group 1. So group 1 will be Alicia, Gracia, and Darren.
Okay, sir.
Alicia, Darren, and Gracia. Okay, you may present your screen. Okay, already. And please turn on your video. Okay. You're still muted, yeah, Gracia. We cannot hear you.
Okay, sir.
Okay, so we are going to answer this question. Okay, so from this circuit, we need to find the voltage across capacitor at 40 more than 0. And the first thing that we need to do is find the voltage across capacitor at the initial state or at time less than 0. And we will find the result by using voltage divider, and the result will be 8 volt. Next.
Okay, so after we find the 8 volts initial voltage across the capacitor, we can go to the next step, which is when it is more than 0 or when it is infinity. So after it is time 0, the switch will be opened, and so the left part of the circuit will be open circuited, and so you can just erase that from the circuit, and so you will get the bottom circuit right here. And then we can use KCL, and we can look at the node VCT. So in VCT, the current will be going from the capacitor, and one will be going to the resistor. And so 100 times 10 to the power of -6 times dVc by dt, which is basically the capacitance equation for voltage, for current, plus the total resistance right here, 6K, plus VCT by the total resistance, 6K, which is equal to 0 because we don't have any forcing function or anything like that. And so we can use the differential equation approach. We can multiply 6K to each of the variables. So 6K times 100 microfarad, which will be equal to 0.6 times dVc dt plus VCT is equal to 0. And from this equation, from this differential equation, we can immediately get our time constant, which is 0.6. And we can also get the K1, which is equal to 0.
Okay, next we can finally use the general equation, which is xt equals k1 plus k2 times e to the power of -t per tau. And since we're looking for VCT, we replace xt with VCT, and before k1 equal to 0. So now we're just left with k2 times e to the power of -t per tau. And then now looking for k2, which equals to VC0, which before we found was 8. So gathering all the information, we get that VCT equals 8 times e to the power of -t per 0.6.
Okay, well done, group 1. Only for the uploaded answer, please thicken the ink and enlarge the size, yeah, so that I can clearly read your answer. Okay.
Yes, sir. Thank you.
So that will leave us with the remaining group 2. So group 2 is Catherine and Elijah.
I'm sorry, sir. Tadi nggak tahu ternyata ininya apa speakernya tadi masih on.
Yeah, okay, it's okay. Please turn on the video, Catherine and Elijah, and you may share your screen.
So this is the circuit, and then the first step is we make the node analysis in this node V0. So V0 minus 9 over 6K plus V0 over 9K plus V0 over 9K minus 2 milliampere is equal to 0. And then we get V0 is equal to 7 volt. Then tau is our equation times capacity.
Can I add something about the tau? So the Here after this, we are going to use the constant, which is RC equals to tau, which is the value obtained by equivalent resistance and capacitance. So that's why
Yeah,
tau
but
is
before you get to this, yeah,
R.
what is the differential equation? The general. Yes, this is complex. Yeah, using differential. So okay, 6K because it like this. Yeah, we don't immediately calculate tau from the R equivalent times C. You have to first express it in the different equation. Tau the circuit, yeah, the tau dx dt plus xt equals to F. Right, from there, then you know that the general solution will be xt equals to k1 plus k2 exponent minus t over tau. So after you express them as tau dx dt over plus xt equals to F, then you can immediately know where you should calculate tau from. Because I see that in the upper part, you immediately calculate tau from the equivalent resistance, yeah.
Yes,
Yes, sir.
C. And I found that the tau is not correct actually, according to my key answer. Okay, please continue first. Yeah.
Okay, sir.
Make it quicker, so because we don't have much time.
After that, we are going to redraw the circuit. As you can see, from that, we redraw it into multiple until we get that circuit. And then we use mesh analysis. And here we use KVL. And then we input the differentiated equation. Then we will get the solution. Tolong yeah. And then after that,
so from here, like the differential equation, you obtain 6K di dt plus I t over 2.5. What is that? Micro or volt?
Micro.
Micro equals to 0, right?
Yeah.
If you want to obtain the tau, then you multiply both sides with 2.5. All the terms with 2.5. Right? 2.5 times 6K. That will be the tau value, right? Tau di dt plus it equals to 0.
Excuse me, sir. Can you repeat it?
Yeah.
Yeah. So, like I have taught you in the previous 2 hours.
Yeah.
So you have to rewrite, to re-express the equation of the circuit in terms of a plus x equals to F, right? So if it is like this still, and you know that you want to find I, I will be X here, right? So the coefficient multiplied to I should be 1. In order to make it 1, it means you have to multiply this with 2.5 micro here. Okay, this is times 2.5 micro. So why the result is like this, right? Should be the result instead 6K times 2.5 micro di dt plus it equals to 0. So from here, you know that this will be the tau of your answer. So because the general solution for tau dx dt plus x equals F will be later xt equals to K1 plus K2 exponent minus t over tau. Like that. Yeah, so simple. So first, but in order that we can get this general solution, we have to re-express the circuit equation into this standard form of the differential equation. And this is not standard because the I, which is x here, still have a coefficient of this, right?
Yeah.
Okay. Anyway, so can you continue?
Okay.
Okay, sir.
So the solution is IT is equal to IC plus IT. which is IC is complementary solution and IP is particularly integral.
Yeah.
Then IP is 0 because the above differential equation has 0 on the right side.
Therefore, we can just input it become ICT equals to IT, which IT stands for K times E to the power of negative T divided by RC.
This is tau.
Yeah. And then we just input our numbers, which is 12 minus 7 divided by 6K, which then we will get 5 per 6 milliampere.
Yeah. And then for the K value, I0 is equal to 5/6 milliampere times A in the power of 0 over RC, which is K is 5/6 milliampere. And then the IT is 5/6 A minus T over 5 milliampere, for T is big greater than 0. So,
and then the IOC equals to 0, which is in a steady state where the C is open. Yeah. And then,
so the T is equal to R times E. R is 6K ohm times E 5/6 A minus T over in the power of minus T over 5 milli. In this case, milliampere. So we eliminate M at 6 and 6, and we get that V is 5E in the power of minus T 0.005 because the 5 milli.
Yeah. So okay. Oh, not yet finished. Okay.
Yeah. So
yeah.
V.
And then for the VOT, we can use the as you can see, 1 per 1 over C integral IT di apa itu tulisannya?
Harusnya di T.
Oh ya, dt. Yeah. And then from there we just input IC integral T to 0, and then we insert the IT, which we get above, which is 5.6. And then after that, we will get 1 over 2.5 micro times 5.6 times 10 to the power of negative 3, blah, blah, blah. And then we will get the final answer, which is the VOT, which are 12 minus 5e to the power of negative t, 0.005 volt.
Okay. So here the K1 value is correct actually at 12, right?
Yeah.
The K2 is also correct.
Yeah.
Minus 5. However, the tau value is wrong.
Oh, okay.
The tau value should be 0.015. Okay. That I suspect some mistake when you immediately.
Yeah.
Calculate tau.
yeah.
Please correct.
Yeah, I see. Where is the
in your uploaded answer later?
Yeah.
So
Okay,
that,
sir.
And yeah, please also follow the appropriate steps. Yeah, so do not immediately tau equals RC, R equivalent MC. So you have to express first the circuit equation in terms of differential equation in the standard form. Yeah, tau dxdt plus x equals to f. From there, you know that the general solution is xt equals to k1 plus k2 exponent minus t over tau. Okay, k1 is do steady state analysis, k2 is from the initial value. Okay, thank you, group 2, for
Thank you, sir.
sharing your answer. with that will be all for today. So the OTP for the third session, yeah, week 4, third session is 2303. Okay, 2303, and please do not forget to what do you call it? Submit, yeah, upload your answers, yeah, and those who need to make revision, please make revision. Upload it to the Google Classroom by tonight, yeah, 23:59. Please do not be late. Each member should, each person should still upload, yeah, but the same group, the members from the same group can upload the same answer. No, it's okay, no problem. Okay.